ASIC system-on-chip design methodology. Emphasis on functional verification. Artificial intelligence. Our ASIC methodology provides multi-million gate designs with 90 nanometer semiconductor technology solutions and system-on-chip development. Functional verification is part of the ASIC design methodology in order to ensure that your design meets functional requirements. Verification process provides for gate-level event simulation, gate-level cycle simulation, gate-level hardware acceleration, and Boolean equivalency checking. Keeping complex verification environments tractable means increasing the level of abstraction. With transaction accuracy, the verification model consists of sequencer, transactions, and drivers. Virtual sequencer, verification components, device under test, DUT, verification components, scoreboard. Methodology integrates a build phase, a connect phase, end of elaboration, start of simulation, run phase, extract, check, report, and final phase. That is part of the verification methodology. On this software verification model, interface design under test, we use the interface to drive the clock driven directly from the top level. The virtual interface comes into play, and the virtual interface comes to a pointer and puts it into the UVM and fixed database. Constrained random verification consists and integrates checkers, coverage, and constraints. There are several phases that makes up the transaction level communication, message, reporting, end of test, and register layer. It can later retrieve other UVM clocks, and then you can start and run the test as shown in this display. Under the engine, build phase, connect phase, and run phase. Gate level simulation methodology, the Verilog simulation with back annotated delays, VHDL simulation, vital compliant VHDL models, and back annotated delays. Verification tools supported are Avanti, Polaris, Cadence Verilog XL, Leapfrog, ICOS, Mentor Graphics Model Simulation, QuickTurn, and Synopsys VCS, as well as Vera. Functional verification for the MAC core is performed with an automatic stimulus generation and randomized testing. Stimulus generation for the Mac controller, the test is divided into three categories: normal, transmit, receive with errors. An important element of the Mac verification process is controlling packet distribution, packet size, the MAC destination address, alignment of errors, and CRC error packets. The network events includes collision. The MAC test bench sends packets in full duplex mode, produces random number generator functions, provides polymorphism, support cycle accurate reference models, and also semaphore registers. There are two main types of formal verification, that is model checking and equivalency checking. In model checking, the verification engineer writes invariants for the DUT design under test. ASIC design methodology consists of VHDL design entry, functional simulation, logic synthesis, timing analysis, IDIF, gate level simulation, test vector generation, and fault simulation. The design entry in Verilog HDL or VHDL describe the identity declaration, the architecture body, the configuration declaration, package declaration, and package body. Functional simulation with vital sign-off simulation and model sim. Chip synthesis allows for translation, optimization, and mapping of your ASIC design. The translation reads and analyzes and elaborates. Optimization to constrain the design, and mapping design database and design IDIF. Analyze performs syntax HDL checking and synapses rule checking. It stores intermediate files in your design library, .sim, .sin, .mra file, each HDL design unit. Need to partition the design for synthesis, separate distinct functions. Implement the design where soft macros such as adders, comparators, etc. System level verification. ASIC SoC methodology. Verification models consists of RTL, memory blocks, and software macros. The physical environment contains the hard macros and hardware test benches. For in-circuit verification, the target system, software environment, debugger, and CVE are supported. Test benches include the Model Sim, VCS, Verilog XL, and the stimulus consists of synthesizable test bench and test vectors. Machine learning and artificial intelligence application. In product development with emphasis in R&D for intelligent drones, global navigation satellite systems, radar. Perform ASIC front-end design methodology for Cisco, IBM, and Motorola system-on-chip, SoC, architectural software model. Universal verification methodology provides the framework to achieve coverage-driven verification. It combines automatic test generation, self-checking, test bench, and coverage metrics. The test bench is composed of reusable verification called verification components. Here I illustrate a verification environment with 3 interface verification components. It can be stored in a repository to be reused later. The interface verification component is instantiated and configured for a desired operational mode. The verification environment also contains multi-channel sequence. It is a sequencer to synchronize timing and data. Data items represent the input to the device under test, the DUT. It includes networking packets, bus transactions, and instructions. The basic level components of a transaction level verification environments are A stimulus generator sequencer to create transaction level traffic to the DUT. A driver to convert these transactions to signal level stimulus at the DUT interface. A monitor to recognize signal level activity on the DUT device under test. An analysis component to analyze transactions. The FIFO ASIC design methodology test bench consists of the test flow, the FIFO device under test, DUT, the read interface, and the coverage monitor. FIFO generator. The FIFO generator core generates fully verified first in, first out FIFO memory queues. The FIFO core provides an optimized solution for all FIFO configurations and delivers 500 MHz performance. It supports FIFO data bits from 1 to 1024 bits, supports independent clock domains. Our sophisticated FIFOs also support error correction, support for packet mode, and supports asymmetric ratios, read-to-write port ratios. FIFO process with randomization coverage. Component declaration. The number of coverage beans. Setting the bus for FIFO. Sending the number of words to the FIFO. Writing to the FIFO. Initializing the generator. Count FIFO transitions. ASIC system on chip design methodology.